calorific value plus 550 divided by 990. So if we try to take this lower calorific value was, take this one. So typically it should be around 1.35 times Yes. So it's close to this one then, but you would, when you make your decisions about the design value in the boiler, you should say, where are we? Is the figures I have been using, is it very high calorific value? Is it very low calorific value? Am I going to make a conservative approach? Is it a less conservative approach? And then you make your design accordingly. But here you have 10.4 normal cubic meter per kilogram of fuel, and perhaps we should try to say what are we talking about when we enter into the boiler? Are we talking, say, 800 centigrade going into the boiler? Then we have to convert this here by so we have to adjust it accordingly, like 20 normal cubic meter at 200 centigrades. We have to convert this to actual cubic meters. So the figure we take, it's not 20, it was this one times actual combustion air demand
is 10.4.
Yes.
Is
but when it's the balance, how to find the balance between primary air and secondary. I try to make people visualize you're making a bonfire in your garden or at the beach, and you just start the fire, smoke is coming, it's not really burning, and suddenly when it's getting heated up, then maybe 1 meter above the bonfire, flames start to come, and that's all the volatiles, all the gases in the fuel being burned. And that's where we need the secondary air. The secondary air is to burn all the volatiles. So if you have coal, trying to look here, with very high carbon, there's very low volatiles compared to biomass. Then here you need a lot of primary air, but when we start talking about biomass with high volatile matter, then we need much more secondary air. And the balance is something you'll have to adjust when you have the fuel. If you have too low secondary air, you would probably start to have increasing carbon monoxide in the flue gas. And then you say, okay, I just put my forced draft fan, I give it higher revolutions, then you will increase your oxygen content in the flue gas, but your carbon monoxide will not come down. It's something with the balance between primary and secondary air. So this is when you make commissioning. Then you have to teach the staff operating the boiler how to look into the flame and look at the equipment you have to adjust the balance between primary and secondary air. I had, when I was a marine engineer, I had a third engineer taking care of the boilers, and then we had inspection coming from the company with a lot of equipment to measure the flue gas. And then third engineer, he said, how much oxygen do you want? Ah, shut up. I give you 8%, and then he went and adjusted the boiler just by feeling it. And then the guy went up to measure, and then he came back, and he was, what's up? How much was it? And he turned around, how much was it? 8%. So you have it, once you work with the boiler, you will come to know how it's working. But of course, you have to work with it.
Perhaps we will also talk about this control of this.
I have on the control, but maybe.
I'm talking about combustion.
Yes. Later, this afternoon.
Lars, I'm afraid we have to cut short right
Okay.
now. We have to do lunch before the Juma prayer.
Okay, yes.
It is on the first floor, the arrangement of lunches. The Juma prayer is at 1:30. Unfortunately, the mosque is located in a police station. So from here you have to go to police station, so nobody can run from here. So after the prayer, we will gather again at 2 o'clock and we will resume the session.
Combustion air demand, including the excess demand, and excess demand is different depending on different fuels, but also depending on different combustion technology. We look at this one here with dust firing. That's where you can have relatively low surplus, coal dust, and here biomass dust. I've seen some dust-fired boilers here in Pakistan, and I've actually been amazed at what I've seen, because it's very efficient combustion burning, and it's pretty simple technology. The only question is how to prepare proper fuel for the dust burning. It might be costly, but now we came up here with actual combustion air demand. Then we had to look into the flue gas, and the flue gas, the wet flue gas, we have this formula here. Again, an empirical formula. Once you have it, then it's easy to use, put it into a spreadsheet like this, and then you just put in the different, here like water, the moisture content, carbon monoxide, methane, depending on your fuel, but it's made even easier here a formula for oil, and here one for solid fuel. And the solid fuel you can use both for coal and for the biomass. L0, the theoretical combustion air amount, the one we were looking at the previous sheet. V0, the theoretical flue gas amount, also the previous sheet. And what we now want to know is the actual flue gas. So we have the theoretical plus air surplus minus 1 times the theoretical combustion air. Here, if it's an oil fired, here, if it's solid fuel fired, and then I made it here, that was L0, the theoretical combustion air, and then we get the theoretical flue gas amount. Then I made it here with Weisshusk, going back again, taking the information from this LCV for the Weisshusk, LCV E15, this figure. So if things are changing here, we can change it here, or when you use it, if you have a setup, you put in the figures you have for your specific fuel, and then you move over here, and then you just change it. It should be pretty easy. If we look at the figures here, 5.9 normal cubic meters, 6.8, 6.7, 10.8. I don't think I've got that. Oh, we have one for oil also. Coal eats quite a lot, or gives quite a lot of air per kilogram. But when I've seen how the boilers are designed, very often what I've seen is, hey, somebody has been looking at a Chinese boiler here and made a profit. I have a friend in Thailand. He has a textile factory, mainly finishing, but he's also got a new dye house. And for his new dye house, he put up Weisshusk-fired boiler from China. And he had a lot of problems having it properly adjusted because it was not designed for that fuel. And when you have the flue gas, you need to know the specific heat. What is the heat in the flue gas? The kilocalories per cubic meter per centigrade. So if you increase the temperature, I have here average specific heat value for flue gas in the range of 2 to 300 centigrade. It's in the range of 0.33 to 0.34 kilocalories per normal cubic meter per centigrade. Then here, furnace temperature should be kept below 1,200 to 1,400. This is basically some biomass. You can go up to 1,000, and some biomass types you should not go above 800 centigrade. And this is something you have to consider when you make the layout of the furnace and the boiler. This here, kilocalories per kilogram fuel, that's over here. And when we talk about biomass, we are in the range here 3,000 to 4,000 kilocalories. And then we have the flue gas temperature. Depending on this here is surplus lambda value, is air surplus. And with biomass, we would typically be here